Hi, Assalamualaikum and good morning. This is my lecture number 8 for CHM 477 Inorganic Chemistry. I'm going to go into the topic of heteronuclear diatomic molecules for this lecture. As you can recall, we went through in my lecture number 7 homonuclear diatomic molecule where the uh, molecule having two atoms of the same type, yeah, that is homonuclear. That's the example would be this is what we have learned previously: the lithium 2, beryllium 2, boron 2, carbon 2, nitrogen gas, oxygen gas, and fluorine gas, and how from this diagram we can calculate the bond order of those molecules and predict whether those are going to be stable molecule or are they going to be able to exist in nature or how. So I'm not going to go through homonuclear diatomic molecule again. If you need any more explanation, just go ahead and contact me in our chat group. Now, for heteronuclear diatomic molecule, as the name suggests, it is also a molecule that is made up, or there are also molecules that are made up of two atoms, but the two atoms are not the same. They are different, heteronuclear, different atom, yeah? There are molecules containing atoms of two different elements. And one of the first example that I would like to give you here is the nitric oxide molecule, NO. Yeah, NO, nitric oxide molecule. Now, for molecules that contain atoms adjacent to each other in the periodic table, such as nitrogen and oxygen, as you can recall in the periodic table, nitrogen is in group 5 and then oxygen is in group 6. They're just next to each other. We can use, because the atomic orbitals of those adjacent atoms are located at almost the same energy level to each other. Yeah, they are of the same energy level. We can use the molecular orbital diagram that we built or that we have developed in last semester in the last lecture for homonuclear molecules, because the energy levels of the atomic orbitals of the two different atoms are not very different. Okay, so this is a simple drawing or a simple representation of the molecular orbital of your nitric oxide. Okay, let me make that slightly smaller so we can have everything in the same page, so easier for us to discuss. Notice that I'm not putting your my sigma 1 and sigma antibonding here, 1. uh, the result of the overlap of the 1s orbitals. We are doing away with that because that is not the valence atomic orbitals that was involved. So we are only discussing the valence. So this is your sigma 2, sigma antibonding 2. Well, this is 2s really. This is not 2s. Something is missing. There you go. There. Something is not right. So I'm not. So look, with 2s. Yeah. Yeah. Sigma 2s as a result of the overlap of the 2s orbitals of the nitrogen and the oxygen. You have your sigma antibonding 2s, which is the destructive interference or the minus overlap. And then you have your pi 2py as the result of the overlap of the pi 2py, pi 2pz, sigma 2px, or this is the bonding pi orbital, this is the anti-bonding pi orbital, this is your sigma molecular orbital, the result of the overlap of the 2px, and then the sigma antibonding result of the overlap of the 2px as well. Yep. So you have sigma 2s, sigma antibonding 2s, pi 2py, pi 2pz, pi antibonding 2py, pi antibonding 2pz, sigma 2px, and sigma antibonding 2px. I hope that those are not unfamiliar terms for you at this stage. Now, if you recall, for nitrogen, there are 5 valence electrons, and for oxygen, there are 6 valence electrons. That means if you have NO, the nitric oxide gas, you have 11 valence electrons. So you have to place 11 electrons in this molecular orbital. Remember, when you are placing the valence electrons in the molecular orbitals, you start from the bottom first. The lowest, you put in 1 and then you pair it up, because it's a lot less, it is more favorable to pair the electrons here than to put another electron there. So you have 1 electron and 2 electrons in the sigma 2s, and then you have 2 more electrons that you can put in the same way in your sigma antibonding 2s. And then for your pi 2py and pi 2pz, you actually put them singly first. Well, this excuse me, I'm trying to, well, just imagine they are occupied singly. This one goes in first and that one goes in later. And then that is electron number 5 and electron number 6. So electron number 7 will pair up with electron number 5. Electron number 8 will pair up with electron number 6. So you have your pi 2py, pi 2pz orbitals filled. You still have 3 more because you have 11, remember? So the next 2 will go into your next available molecular orbital, which is your sigma 2px. 1 and 2 there, and then one single one electron, because there are 10 down here, there's one more that you have no choice but to put in the pi antibonding 2px, 2py and pi antibonding 2pz in this manner. So as you can see, you have an unpaired electron for nitric oxide. So it is a paramagnetic molecule. Paramagnetic because it has one unpaired electron on the sigma and antibonding 2p, either 2py or 2pz, it doesn't really matter. Now, when you count the bond order, it's really very easy. If you remember the formula for bond order is the sum of bonding electrons, which are 2, this is not them, so 2, 4, 6, 8. 8 minus the sum of antibonding electrons. So your antibonding is 2 and 3. So 8 minus 3, you have 5. So divided by 2, you're going to have bond order of 2.5. So nitric oxide is quite a stable molecule because it has a bond order, a high bond order of 2.5. So we can use either the molecular orbital of N2 or O2, since nitrogen and oxygen do not have very different atomic orbital energy levels. So if you look at this arrangement here, you can either, okay, let me go down. You can either use this arrangement for nitrogen, where you have pi under the sigma, or you can have for oxygen where you have the sigma under the pi. Both are equally all right for you to use, yeah? The highest occupied molecular orbital, the HOMO, is the pi antibonding MO, this one here. Therefore, taking away one electron will from NO will make NO plus and will produce a stronger NO bond. Yeah, if you take away this electron in the HOMO, this is your HOMO, you are going to make the bond order of 3 because that would be 8 minus 2 divided by 2, 3. So bond order of NO2 will be higher than bond order of NO. So you have that situation happening. So if you are asked to evaluate or predict the bond strength of NO compared to NO2, then that's how you do it. So that is about nitric oxide. So your LUMO in the case of NO is your sigma antibonding 2px. No, no, no. Your LUMO is here. So if you have to, uh, if NO has to take pi back donation, or this is not in your syllabus yet, if this molecule has to add electron in it, it's going to add 1 electron in here. This is your LUMO, yeah? This is your HOMO, this is your LUMO, or and they happen to be in the same level, energy level. So that's fine, no problem. Yeah. So calculating the bond order will give you an idea how strong that species is going to be. Yeah. And O with the bond order of 2.5 is a less strong bond, has less, it's a weaker bond than NO plus because NO plus will have a bond order of 3. Yep. So I hope that is clear. So I'm going to go next into the something heteronuclear diatomic molecule as well, but this time you cannot use the molecular orbital like this because the atomic orbitals of HF, yeah, hydrogen fluoride, they totally have different energy levels. There is no way that the energy level of hydrogen and energy level of atomic orbitals of fluorine to be the same because they are far away from each other in the periodic table. So let's discuss what happens and how you are going to draw the molecular orbital for a heteronuclear diatomic molecule of a molecule having totally different atoms. Yeah. For example, we have hydrogen fluoride, where the electron configuration of hydrogen is 1s2, and fluorine, the electron configuration is 1s2, 2s2, and 2p5. Totally different energy level. Now, to simplify the discussion, we can assume that fluorine only uses its 2px orbital to bond with the 1s orbital in hydrogen. Why do we say it's using the 2px? Because the 2py and 2pz orbitals will not overlap effectively with the 1s orbital of your hydrogen, because the 1f orbital has a sphere shape. This is your 2px in this orientation, so it's a good head-to-head overlap. But if you have 2py, maybe in that way, I don't know if you can see this, it's like doing karate, they're not going to have a very good overlap there. Yeah. Now, the atomic orbitals of F are located at lower energy than the 1s orbital on H because fluorine has a higher effective nuclear charge than hydrogen. Now, fluorine has more protons in it, so it's heavier. The energy levels of the orbitals will be located at a lower energy level than the 1s because the hydrogen has only one electron, one proton. It's not that heavy. It has quite, the energy level of 1s is quite high. So this is how it looks like. This is your atomic orbital of your hydrogen atom with the 1s1, one electron in the 1s orbital. And then this is for your fluorine. The atomic orbitals of your fluorine is this is the valence only. We don't have to deal with the inner. So you have the 2s, 2s2, and then 2p5 electron configuration. So they are definitely located at a lower energy level than your 1s. Now, because the overlap is not going to be effective between the 1s and the 2s, because the 1s, even though the shape would be good, the shape, this is round, that is round, the shape is good, but the energy levels do not match. This is a high energy level, this is a low energy level. It's not going to have an effective overlap. So your 2s is simply going to become a non-bonding molecular orbital. Yeah, in the molecular orbital is simply going to become a non-bonding. This is just, sorry, excuse me. Oh, just like that. Yeah, that's better. Yep. Hmm. Your 2s, because it cannot overlap with anything, is simply going to exist as a non-bonding molecular orbital, just lower in energy than the parent 2s. And your 2px, this is your 2px, and this is your 1s. Even though it is still at a lower energy level, it can still overlap because the difference in energy is not that great. The geometry is correct. The energy levels are not too different. So you have a good overlap between your 2px with your 1s, your 2px of fluorine with your 1s of hydrogen. So you get a sigma 1 and a sigma antibonding 2. You cannot say here that this is sigma 1s like the one that you see at the top here, or sigma 2s, because these two, this is the form from the same 2s overlapping with 2s. But in the case of this, your 1s is overlapping with your 2px, so you just simply call it a sigma 1. And then the antibonding molecular orbital is called a sigma 2, sigma antibonding 2. And then what else? You have these two, 2px, 2py and 2pz. They are not having anything else to overlap with. So they simply again become a non-bonding molecular orbital like this. So you have one non-bonding molecular orbital from the 2s and another two non-bonding molecular orbital from the 2py and 2pz, and you have one sigma bonding molecular orbital and one sigma antibonding molecular orbital for HF. And how many electrons do you have to fill in the molecular orbital? You have one electron from the hydrogen and you have 7 electrons from the fluorine. Valence, we only count the valence electrons. So you have 7 and 1, you have 8. So the way that you would fill 8 electrons in this arrangement would be 2 at the very bottom here, 2 more at the second highest, and 4 more at the degenerate non-bonding molecular orbital in here. So you have all the electrons paired up. Hydrogen fluoride is not paramagnetic. It is diamagnetic. Now, other atomic orbitals on F will become non-bonding. This one, the 1, 2, and 3 will become non-bonding molecular orbitals, and other valence electrons on F remains localized on the fluorine. That means this black electrons that I draw in black, they are localized on fluorine. They are very heavily attached to the fluorine, even though it has made a bond with hydrogen. Yeah. HF molecule should be stable because the unpaired electrons from both atoms are lowered in energy relative to their energy in the free hydrogen and fluorine atom, and this is the driving force for the bond formation. Because all of these filled molecular orbitals in here are in lower energy levels compared to the atomic orbitals. That's why it is most favorable for HF to exist as a molecule rather than a single H and a single F. They would very much prefer to exist as a molecule of HF. Yeah. Because the fluorine 2p orbital is lower in energy than the hydrogen 1s orbital, the electrons prefer to be closer to the fluorine atom, i.e. the sigma 1 molecular orbital containing the bonding electron pair shows greater electron probability close to the fluorine. Because here you have fluorine is lower in energy, this one here will be if the electron density is being mapped, you will see that this is located closer to the fluorine, not closer to the hydrogen. The electron pair, okay, and the sigma 1 molecular orbital containing the bonding pair shows greater electron probability close to fluorine, which I have read, and the electron pair is not equally shared. Yeah, the bonding electron pair is not shared equally, giving rise to the polarity observed in HF. Yeah, you can also explain this polarity through electronegativity of fluorine. We know that fluorine is the most electronegative atom in the periodic table. So the HF bond is highly polar, where the electrons are most of it located close to the fluorine, the more electronegative fluorine. And if you draw the Lewis representation of HF, it is very, very consistent with the molecular orbital diagram that we draw here. Yeah, because this is low in energy, it is very close to the fluorine. It is not very close to the hydrogen. Yeah. So the Lewis presentation of hydrogen fluoride is consistent with the molecular orbital treatment, this drawing. That is, one bonding pair of electrons is shared between the HF. This is your bonding pair of electrons that are being shared between the hydrogen and fluorine, which is the electrons drawn in red here. And three lone pairs of electrons or non-bonding electrons are associated with fluorine. One pair, two pairs, and three pairs. The three non-bonding lone pair of electrons are actually belonging to the fluorine. So that's it. Those are two examples of two extremes of heteronuclear diatomic molecule. The first extreme is when you have your nitrogen and oxygen having adjacently located in the periodic table just next to one another. So you can use this very familiar looking molecular orbital that you have learned to draw in the previous lecture. And another case is when you have a diatomic molecule heteronuclear with the atoms being far away from. It's very, very noisy outside. The LRT3 people are driving me mad. Never mind. Ignore the LRT3. So when you have hydrogen and fluorine bonding, each one having energy levels totally different from one another, you're going to have something like this happening. Yep. So that just about wraps up our heteronuclear diatomic molecular orbital treatment. Now, coming on to the next topic. Okay, the next topic is metallic bonding. I'm just going to combine this in this lecture. I don't want to break it into two different lectures. So metallic bonding. So metals, yeah, everybody doing chemistry know the general characteristics of metals. Metals are characterized by being lustrous. What does lustrous means? It means it's shiny. It has luster. Macam if you listen to many advertisement about good skin, lustrous skin, and like that, it is like bersinar-sinar, ada nur begitu, ada nur, lustrous. Possessing high electrical and thermal conductivity, metals are very good electrical and thermal conductors. Substantial malleability. Malleable means you can knock them and make it out of shape. You can change the shape off the metal just by knocking with hammer. That's malleable. It means it can be molded. And metals have relatively low ionization energies. Now, physical properties of metals, such as the boiling point, very high boiling point, usually for many metals that we know, melting points and hardness depend on the strength of the bonding in the metal. So whether you're going to have a metal that can flow like the mercury, or if you're going to have a metal that is soft like sodium that you can cut, or if you're going to have a metal that is hard like iron, for example, they all depend, the property, the hardness and the boiling point and the melting point all will depend on the strength of the bonding in the metal itself. So when we are discussing about bondings in metal, there are two models that people always talk about. The first model would be the electron C model, which is the most common and the crude way of explaining metallic bonding, by assuming that the metallic lattice is composed of closely packed positive ions surrounded by an electron cloud. This is how you would explain electron C model. You have your sodium, for example, yeah, closely packed positive ions. The ion of sodium packed very closely together, and they are surrounded by electron cloud. Where do the electron cloud comes from? Comes from the electrons, the valence electrons. These are the sea of valence electrons. So for sodium, you have, for each one atom, you have one valence electron, because sodium is 1s2, 2s2, 2p6, and 3s1. Can you recall? Yeah, sodium is, if you look into your periodic table, you're going to see that sodium is the first element in the third series. So you have 1s2, 2s2, 2p6, and 3s1. So that is sodium. And your valence electrons for sodium is 1. So for each one sodium atom, you have one valence electrons. So it is the valence electrons. This happens when the neutral atoms lose their valence electrons, forming metal cations, and the non-localized mean they don't stay in one place. The non-localized valence electrons build the electron cloud, which belongs to the entire crystal of the metal. The attractive force between the electron cloud and the positive ion is called the metallic bond. So the strong bond that exists in metals actually is the attractive force between the positive ions of the metal with the valence electrons that are located around the positive ions. And the metallic bond will hold the crystal of the metals together. Now, an illustration of this explanation is given below in here, using sodium as an example. So you have here the electron cloud surrounding positive metal ions Na plus in the sodium lattice. Yeah, so that is the electron C model. In fact, you can really see why it is called the Lautan electron, or the sea of electrons, because these are like islands, and the electrons are like a sea around them. Now, the strength of the metallic bond is inversely proportional to the size of the ion. The smaller the size of the cation, the stronger the attractive force between the positively charged ions and the electron cloud. That means the stronger the metallic bond. So if you have a very strong attraction between this negative C electron C with this positively charged cations, then you're going to have a strong metallic bond. On the other hand, the strength of the metallic bond is directly proportional to the number of valence electrons on the metal atom. Each one sodium atom, which is in group 1A, loses one valence electron. to build the electron cloud and form the sodium plus ion, like I explained earlier. But when we move to group 2A, each magnesium will lose 2 valence electrons, forming 1 magnesium 2 plus ion. And when we move again to the group 3A, moving along, each aluminium loses 3 valence electrons, forming 1 aluminium 3 plus ion to build up this electron cloud. The more electrons swim in the electron cloud, the stronger is the attractive force, which is increasingly positively charged metal ions, and that means it will make a stronger metallic bond. So, sodium will have a metallic bond which is weaker than in magnesium, because the metallic bond of sodium is made up of attraction of 1 valence electrons with 1 positively charged sodium. But when you go to magnesium, you're going to expect to have a stronger metallic bond and a harder metal, because you're going to have 2 valence electrons per sodium to make interaction with the magnesium 2 plus center. And moving along to aluminium, which is the element next to magnesium, you're going to have 3 valence electrons swimming in the sea surrounding the aluminium 3 plus. So you're going to have as the strength of the metallic bond increases, yeah, the more electrons attracting, the strength of metallic bond increases. The value of the physical properties such as the melting point, the boiling point, and the hardness of those metals will also increase. So it is therefore quite easy to explain why sodium is a softer metal compared to magnesium, and why magnesium is a softer metal compared to aluminium, and vice versa. Aluminium is harder than magnesium, magnesium is harder than sodium. The melting point of aluminium is the highest, the boiling point of aluminium is the highest when you compare the 3. That is because aluminium has the highest metallic bond, the highest metallic bond. So, in metals, now this is the C electron model, electron C model. Now, sometimes electron C models can be used very effectively to describe the hardness, the softness, and everything of the metal, but it cannot explain effectively a few other things. Now, let's then move on to the second model. Yeah. In metals, the electrons are present in large number, and they move in a high velocity, which accounts for the high thermal conductivity of the metal. Yeah. As you can see here, the electrons move. They can move. Electrons do move. They do not stay in one place. So because the mobility of the electrons, metals are very, very good thermal conductivity, very, very good electrical conductivity. The high velocity of movement of the electrons make them a much more efficient means of transferring heat energy, and the atomic vibration that are only other mechanism for heat transfer in the case of other solids. Yeah. Now, the presence of conduction electrons act as a sort of free electron gas. It's like a floating electrons, like a gas around us. Yeah. In real life, we have gases, oxygen, nitrogen, carbon dioxide floating around us. So in metal, you can imagine that those electrons are like free electron gas within the metal crystal, which allows them to interact with oscillating electromagnetic field of visible light in such a manner that the light is totally reflected, giving the familiar lustrous appearance of metal. So when those electrons move and they interact with the oncoming ray, visible light, electromagnetic field, totally reflected by the moving and forever mobile ions, you're going to see the luster, the shine of the metal. Yeah, so you can explain using the C electron C model, the thermal conductivity, the softness, the hardness, and also the lustrous appearance of the metals. Yeah. And as I was saying to you earlier, a successful bonding model for metals uh, must be proposed to account for the typical physical properties of metals, such as efficient and uniform conduction of heat and electricity in all directions, as well as the metallic luster. Although the shapes of most pure metals can be changed relatively easily, most metals are durable and they have high melting points. This fact indicates that the bonding in most metals is both strong and non-directional. Non-directional means it can go in whichever direction. If you knock it this way, it will go that way, and so on and so forth. Now, as I have explained to you earlier, the simplest picture that explains this observation is the electron C model, which envisioned a regular array of metal cations in a cloud of valence electrons. The mobile electrons can conduct electricity and heat. This is another repeat, but there is another model. There is another related model that gives a more detailed view of electron energies and motion, which is called the band model. Yep, this is called the band model, or sometimes they're known as the molecular orbital model, like the one that we were discussing above, before this, about the molecular orbital. Now, go back to molecular orbital. When two atomic orbitals interact, of course, you're going to have a bonding and you have a you have an anti-bonding molecular orbital. Agree? You have a bonding and anti-bonding molecular orbital. That is in what we understood through the molecular orbital model. Two widely spaced molecular orbital energy levels called the bonding and anti-bonding will be formed when many metal atoms interact. As in a metal crystal lattice, a large number of resulting molecular orbitals become more closely spaced, and they will finally form a virtual continuum of levels called band. So if you have one atom, you have one bonding and one antibonding. But in 1 gram of metal, you have so many number of atoms, because 1 mole of sodium has 6.02 times 10 to the power of 23 number of atoms, Avogadro's number. So 1 gram of any metal will have not only thousands, not millions, not trillions, not zillions, but many atoms. And these many atoms, when they each will make a bonding molecular orbital and anti-bonding molecular orbital, when they are overlap one on top of another, just like when you have lidi, you have one lidi, it's just very thin, but when you put too many sticks together, they will make a band. They will make a strong, continuous band. Similar with your atomic orbital or your molecular orbital, you're going to get, when you have too many atoms uh, in a sample, they make molecular orbitals overlapping one on top of another will make a big band. Yeah, they're called band. For example, in magnesium lattice, the number of atoms in even a small piece of magnesium metal is very large, on the order of 10 to the 20 number of atoms. I mean, in the world, we only have what, 6 billion human, 6 billion. That is only six. Oh, 6000, that is 1,000. Another 000, that gives you million. Another 0009, 9 zeros to make the whole number of humans in the world. But 10 to the power of 20, that is a lot. So Therefore, the number of molecular orbitals they form is also very large. Each magnesium atom has 2 valence electrons in the 2s orbitals, and the 2p orbitals are empty because your magnesium is 2s2. Your 2p's are all empty. So, when many of these orbitals interact, two types of bands can be formed. You have a valence band where the energy levels are filled with electrons. In the case of magnesium, these bands are made up of the 3s orbitals, and you also have the conduction band. The conduction band is empty energy levels. For magnesium, this conduction band is formed by the overlap of the empty 3p orbitals. So, if you have a valence band and the conduction band happening like that, trillions, zillions of bonding molecular orbital and zillions of non-antibonding molecular orbital make these bands. For metals, there is no gap between the valence band and the conduction band. Yeah, I'm going to go back to this later. I'm going to go on. Finished. Now, when you have valence band filled with electrons, and they are located touching one another with the conduction band, it is very easy for electrons to go up onto the conduction band and move. This is like a small road that is filled with cars. This is like a highway, an empty highway. So these electrons can go to these empty bands and they can move, because there is no energy gap between the valence band and the conduction band. That is why metals are good electrical conductor. In materials called insulator, I'm going here first. Insulator like wood, like glass, yeah? Valence bands are separated from the conduction band through a large energy gap. Yeah, there is a large energy gap between the valence band and the conduction band for an insulator. That is why the electrons in the valence band for insulating materials cannot go very easily onto the conduction band. So they cannot let electrons move, so insulators are non-conducting, cannot conduct electricity. Whereas there is a type of material called semiconductors, where the energy gap between the valence band and the conduction band is quite small. Given excitation energy, maybe through heat or maybe through photons, some electrons from the valence band can jump onto the conduction band, but you have to provide some energy for those electrons. And that's what semiconductors do. Semiconductors, when you provide enough excitation energy for the electrons to move from the valence band to the conduction band, then they can start to become conductors. So this is the simple explanation why insulators do not conduct electricity, because of the very large energy gap, and why semiconductors only can conduct electricity on certain conditions or on certain excitation. Yep. So in metal, there is no energy gap between valence band and conduction band, making it very good conductor. In semiconductor, you have a very small energy gap between valence band and conduction band. But in insulators, you have very large energy gap between valence band and conduction band. So this is the comparison of energy gaps between valence band and conduction band in metal, semiconductor, and insulator. That explains the conductivity of these materials. So that's just about conclude my lecture today. So in this lecture, I covered heteronuclear diatomic molecule, the molecular orbitals of similar atoms that make molecules or totally different atoms that make molecule, and then I went on to explain the electron C models that explains the hardness, the softness, the conductivity, the luster of the metal, and lastly I explained to you the band theory of metals that gives a good explanation why the behavior of metal is very different from insulator and semiconductor. Yep, I hope you've got everything that I have tried to relay in this lecture, and I hope you're keeping safe, you're studying well, and take care. I'll see you in my next lecture. Bye bye. Assalamualaikum.